So now we get to inverse functions. And inverse functions are, there's a lot to inverse functions, not all of which we have to do here. These are actually, under the SOLs, considered the essential learnings that we're supposed to get to, right? Find the inverse of a function. Use a composition of functions to verify two functions are inverses. Okay, that's why we needed to do composition before we get to this point. And then graph the inverse of a function as a reflection of across the line y equals x. So we'll do precisely this stuff here, right? We're not going to try to do everything that we could ever do. You'll get more of that later if you go on to later classes on this track, right? But here's the thing about inverse functions. You've done them before. Can anybody think of a time you might have done an inverse, used an inverse function? I'll remind you. What's that? Nope. You didn't do them in this class. I mean, in a way you did. When we square a square root, that's using inverses right there, right? But here's where you used an inverse function, right? See if you can remember way back to the glory days of geometry. Right triangle trigonometry, okay? So remember, you used to, they would either give you an angle in one side or two sides, and then you had to find the angle. You know, you had to kind of like put together, you know, the parts that you were given and then solve in any way you can. If you had angles that were 45, 45, 90, you had formulas for that. If you had a 30, 60, 90, you had a formula for that. But if they weren't those precise angles, you use trigonometry, right? And remember the trigonometry, depending on what you were given, but you would say, okay, I'm being given an angle right here. And then you would have to, based on the sides that you're given with respect to that angle, pick either a sine or a cosine or a tangent function to solve. Remember, how did you remember which one to use? Maybe you did SOHCAHTOA. Remember that? Did you have any funny rhymes to help you remember it? Come on, you guys up in York County are boring. Some old horse came a-hopping through our alley. Never heard that one? Some old horse caught a horse taking oats away. Those are just ways to remember those letters in order. I think some people, I mean, this is really not the point of what we're doing today, but, you know, we're reminiscing. Some people just kind of pronounce it, SOHCAHTOA, you know, maybe that gets you the letters in the order that you need, but before you can use that, you've got to, like, with respect to the angle that you're given, you've got to designate these sides as either being opposite, adjacent, or hypotenuse. Now, the hypotenuse of a right triangle does not change. So I would label this side as hypotenuse. And then this angle, which has got the x degrees in it, the opposite of that is the 23. So I'm going to call that opposite. And then adjacent means right next to. So right next to the x degrees is adjacent. So you would have to say to yourself, which two of the three sides am I using here? This 23 and 34, they are opposite and hypotenuse. Okay, well, based on sine equals opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, you would say, well, this is going to be a sine function, right? So I would say the sine of the angle, the sine of x degrees equals 23 over 34. Okay, now we have to solve for x, but the x is inside of a function. How do we solve for the x? You can't divide by sin, right? It doesn't work that way. This is what you did. You may not remember doing it, but you did it this way. You took the sine inverse of both sides. Sine, and you used a little -1 of the sine of x equals the sine to the minus 1 of 23 over 34. And you probably didn't even see that part of it, right? But here's what we learn is this is a composition. When you take a composition of a function and its inverse, they cancel each other out, and all you have left is x. So actually, x is going to equal the sine inverse. And I hope this comes up this time. I know we don't have the calculators in front of us, but you know, above the sine, it says sine minus 1, and that's what you use to solve these. How many remember doing that? Okay, so you were using inverse functions to do that, and the characteristics of inverse functions. So it's not the first time you've seen it. Now sometimes we need inverses to solve equations. The kind of functions they're called transcendental functions. Transcendental means you can't solve them by just doing algebra to both sides, right? So the only way to solve for a variable which is inside the function is you need another function that undoes the first function, and that's called an inverse. So after we do this lesson, then the next lesson is exponentials, and the next one is logarithms. And those two are inverses, and they're transcendental, meaning you can't solve a logarithm by adding and subtracting the letters log to both sides. You need a function which is the inverse, something that undoes it, and that's an exponential. They undo each other. So let's see what's next. So this is the basics of what is an inverse of a function. Now, this function here is just a table of values. There's 3 points in it. They don't mean anything. They don't necessarily fall in the same straight line. Oh, they do. But here's the function, right? 1, 3, 2, 6, 3, 9. The inverse, which is also like the sine minus 1, designated the little superscript of minus 1, is 3, 1, 6, 2, 9, 3, meaning you just take these two and you flip them. That's the inverse. So if I say f of 1 equals 3, then f minus 1 of 3 equals 1. Right? They go in exactly opposite directions. Right? Which means, just notice the numbers here and understanding what domain and range are. The domain of the function is the range of the inverse. And the range of the function is the domain of the inverse. We ready? So now let's say I graph both of those on the same background. They're just points, right? They don't even necessarily represent lines. So I graph the first 3 points, 1, 3, 2, 6, and 3, 9. And then I'm going to change colors because I can. And I'll graph the inverse, 3, 1, and 6, 2, and 9, 3. If you graph those, it should look like they are reflections across the line y equals x. This line, y equals x, also known as the identity function, right? Because it's 0, 0, 1, 1, 2, 2, 3, 3. That's like a line of symmetry between these. It should look like, you can tilt your head to be 45-degree angle. These completely flip over to this. Right, that's what happens when you just switch the coordinates of 2 points, right? 1, 3 becomes 3, 1. That's actually all it's doing. It's flipping it across that line. What would happen if we had a point on this line which was actually like 0, 0? What would happen when I flip the coordinates? It's the same point, right? So if a point starts out on the line, it's still on the line, of course. But if a point's not on the line, it's reflected exactly across that line, like a line of symmetry. So that is like the second, actually I think that was the third of the 3 essential learnings of from the SOLs. But we should understand that. Okay, now let's say I've already graphed these 5 points, and they come from the function f of x equals x squared, which I could definitely connect, right? Because that is they represent just points on the graph of a function. Oh, I didn't want to do that. I want it to be blue. So this looks like now the inverse again, how do I find the points that go on the inverse? I just switch the coordinates, right? 4, -2, 1, -1, 0, 0, 1, 1, 4, 2. And then I graph those two. I graph those points. 4, -2 would be here. 1, -1, 1, -1, 0, 0, 1, 1, and 4, 2. Do we see the shape? Kind of looks like this. Right, does that look like they might be reflections over the line, the y equals x line? I don't do a very good job of this. That's pretty close. Do they look like they could be mirror images on this side and on this side? Pretty good. Yeah. Oh, 1, 2, 3, 4. You're right. Thank you. So let me go back and make it right there. Thank you. So we understand now the graph of a function is inverse. It should look like it's flipped across that line, y equals x. Okay, now here's the first of those 3 essential learnings. How to find the inverse, right? There's 4 very concise steps here. You have to memorize them. Okay. Right? If you're given a function as f of x equals, then you need to replace the f of x with a y. You know, sometimes we're given y equals. That's fine. Then you don't have to change anything. But if it starts with f of x equals, make it y equals. And then you switch the x and the y. right? Since it was solved for y when you started, when you switch the x and the y, it's no longer solved for y. Y is in the middle of the expression on the other side. So the next step is solve for y. And when you solve for y, that is the inverse. So then last step would be replace the y with f to the minus 1 of x. Okay, so let's do a couple. Find the inverse, and then we're going to graph them both. So first step, and the steps are at the bottom right. The first step is read it. Substitute. Since it's starting with an f of x, let's make it y equals 2x minus 3. Second step. Swap the x and the y, right? Put an x here. And the y on the right-hand side. Okay, now because we moved the y into the middle of the right-hand side, we've got to solve for y, right? Add 3. Divide by 2. Which is f to the minus 1 x. Now for the purposes of graphing, because these are straight lines and I'm going to graph them like straight lines, I'm going to also write it like this. 1/2 x plus 3/2. So that's how you find an inverse, right? Four very concise steps. Now let's graph them. 2x minus 3 is a straight line, has a y-intercept of -3, has a slope of 2. So it should look like this. Okay, 1/2 x plus 3/2 has a y-intercept of 3/2 and a slope of 1/2, which would mean up 1 over 2. Up 1 over 2. So that'll look like this. Now, do those look like that they are reflections across the line y equals x? Pretty close, considering my sloppy drawing. At -3? Well, it should be, because the y-intercept is -3. And this should have an x-intercept of -3. I mean, it's not, my drawing isn't exactly that accurate, but yeah, that's the blue line. Is that? All right, this is the f minus 1. And this is the f. I don't need to say that, that's already there. And this is the y equals x. What do you mean? I'm just graphing a straight line. Y-intercept is -3, the slope is 2. Up 3 plus up 2 over 1, up 2 over 1, up 2 over 1. I mean, it's just straight lines. This one is from 3/2. Slope is 1/2. Up 1 over 2, 1 over 2. Okay, I think it's your turn. Try to find the inverse of that one. Try to do just what we did on the last one and make a graph. So if I get to the point where I've got x minus 5 equals 1/2 y, how do I solve for y? Multiply times 2, right? There's a lot of mistakes going around where we have trouble figuring that one out. So if I multiply both sides times 2, this becomes 2x minus 10 equals y, which means f minus 1 of x equals 2x minus 10. So I'll do the blue. Blue will be the function, 1/2 x plus 5. Right? It means y-intercept is 5. The slope is 1/2. Right? Up 1 over 2. Up 1 over 2. So it should look something like that. And for the inverse, the y-intercept is -10. I think that's like barely on my slide. It's about right there. And the slope is 2. Up 2 over 1. See if I can draw that. Right, that's the f minus 1. And again, just to show, do they look like they could be flips across that line? Not the way I've drawn it. That's pretty good. Does it look like they're flips across the line? Pretty good. Close enough for government work, as we say. Us government workers. Okay, now here's the third part, right? The third essential learning is then we have to verify, show two functions are inverses of each other by taking the composition of them. And it should be, whether you do it f of f minus 1 or f minus 1 of f, whichever order you do it, it should be that everything cancels and all you're left with is x. I mean, that's why when we did the sine inverse of the sine, we just got an x when we were done, right? Because of this property right here. Now, it doesn't always work. We'll talk about when it works and when it doesn't. But let's go through the motions here anyways. So first, this is what I'm trying to do. It's on the top of the slide right here. I'm trying to do f of f minus 1. That's a composition, right? I could write it with that little open circle in between, but I'm not. I've already got it in the function notation. Right, so the first one is f of f minus, or f, sure, it's a bad one. F of f minus 1 of x, replace the f minus 1 of x with what it equals. And then evaluate, how do you find f of x plus 3 over 2? Well, here's the f function. You put x plus 3 over 2 in the place of x there. Right? So that'll look like 2 times x plus 3 over 2 minus 3. Now, do you see the 2's are going to cancel? So that we just get x plus 3 minus 3. And now the 3's cancel, so we have x. Right? That's the first hoped for result, right? But it's not done, but that's what we needed to happen. Now we need to reverse the order of these. It should work no matter which order you do it in. Remember, this is practice doing compositions from the homework last night. Replace the f of x, because now that's the inner function, with what it equals. F minus 1 of 2x minus 3. And then evaluate the f minus 1. Put that 2x minus 3 in the place of x right there. Right, that'll look like 2x minus 3 plus 3 divided by 2. Right, now the 3's cancel, and I have 2x over 2, and the 2's cancel, and now I get the x. So when two functions are inverses, that's what should happen. So the kind of problem you can get with this is they may give you two functions that you didn't just derive and say, show that these are inverses or if they're not inverses. So you're supposed to take the composition and see that everything cancels. Right, so this is the proof that they're inverses. Now there's actually a condition for this that we'll see. I think it's in the next. Actually, I think the next is for you. Right, these were the two functions that you got when you found the inverse. And I called one of them f of x and one of them g of x. So do the compositions in both orders and see whether everything doesn't cancel and all you get left is x. They should simplify. I think in the homework there'll be a few. They'll say, verify that they're inverses. I didn't check all the answers. Some of them may not be inverses, right? So you just have to do it, see what you find. find the inverse, and then graph. Okay, so this is one for me. So this is y equals x squared minus 2. X equals y squared minus 2. Y squared equals x plus 2. And then how do I solve for y? Since it's y squared equals, and we've done this before when we were solving quadratics by taking square roots. First you solve for the squared, then you take the square root of both sides, right? But what do you have to remember to include when you take the square root? Plus or minus, right? So this is going to be plus or minus y equals plus or minus the square root of x plus 2. F to the minus 1 of x equals plus or minus the square root of x plus 2. Okay, so for the graph of x squared minus 2, that's a parabola, right? That's a simple parabola. It opens up because the leading coefficient is positive. It has a y-intercept of negative 2. So I can sketch that in. It will look like something like that. Now, we're not that familiar with what the square root of x plus 2 ought to look like. I mean, the parent function, y equals the square root of x. That's the parent function, and it looks like this. I mean, you could plot a few points, right? It would have 0, 0. It would have 1, 1. It would have 4, 2 on it. So just given that the parent function of a square root looks something like that, how does it shift the graph that you added 2 inside of a function? Something we did in this unit. Left 2, right? So we would expect that our parent function here is moved 2 to the left. So I can take that, add it to the graph up here, 2 to the left. Again, it should be 1, 1, and 4, 2. No, 1, 1, 2. Yeah, that's right. So this looks like that. But that's not the whole function because it's also a minus on that. Well, what does it do to the graph of a function when we stick a minus in front of it? It flips it. So we not only get this graph here, that's the plus, we also get the minus, which is the flip. So it looks like this. Right? Something like that. Straight line? No. Now, do those look like they could be flips across this line? Pretty close? You know? That, and that, and that, and that. It looks pretty good, considering I'm hand drawing these things. Okay, now let me do the next part. Let me do the compositions to verify that these two are inverses. Okay, so hang on to your seats. F of f minus 1. Is that what I want to do? Yeah. Of f minus 1 of x equals f of plus or minus the square root of x plus 2. Okay, so now I have to take this plus or minus the square root of x plus 2 and put it in the place of x there. Right? So that looks like plus or minus the square root of x plus 2 squared minus 2. Well, what's going to happen when you square a plus or minus? It'd be positive no matter what, right? So it actually gets rid of the plus or minus. And what happens when you square the square root? Yeah, I mean, actually, those are inverses of each other. They cancel each other out. So this whole thing becomes x plus 2 minus 2, which is x. Right? That's the first half of what we needed. Now let's do the other. F minus 1 of f of x equals f minus 1 of x squared minus 2, right? And that is plus or minus the square root, and then in the place of that x, I'm going to put x squared minus 2, right? Which is plus or minus the square root of x squared, which is plus or minus x. Now, is that the result we were looking for? No, because it has to equal x, not plus or minus x. It has to equal x. So when we found the composition of these two, it actually did not tell us that these are exact inverses, and they're not, okay? And that's because there is a condition on, I got to remember if I've got it on my next slide, that you can only do that, f of f minus 1 and f minus 1 of f equals x. That's only going to work provided the f and f minus 1 are both functions, okay, both functions. I'll go back to the graphs of these two. One was in red, one was in blue. The blue graph here, right, a parabola opening up, does it pass a vertical line test? The blue graph? Sure, that's a function. How about the red graph? Does it pass a vertical line test? No, it's going to cross in two places all over the place. So, no, it does not pass it. That f of f minus 1 and f minus 1 of f equals x, that only works if both are functions, and they're not both functions. Okay, why did it work on the one before? Right, go back and look at the one that we did before. You know, look at the function graph. It's a straight line. Does it pass a vertical line test? Does this pass a vertical line test? Yeah, they're both functions, so it's going to work. Okay. Now, there is actually a test for this, that usually what you do is you check to see whether your function has an inverse before you find an inverse by going through those steps. Yeah. A function is something that for every input, there's one output. So generally, this is what you do. You do let's say all you've got is the graph of your function, and you could definitely see it's a function. If you want to know whether the graph is going to have, or that function will have an inverse, you not only do a vertical line test, you do a horizontal line test. And would this pass the horizontal line test? No, so you wouldn't even find the inverse because it doesn't have one. Right? We wouldn't be able to do like I did with the sine of sine minus 1 and expect that things cancel out and all you get is x, because it wouldn't, not in this. Okay. So find the inverse of that one and graph. So you should have replaced the f of x with a y, switched the x and the y, solved for y. And again, you're going to get a plus or minus the square root. Right? Now, we just said the parent function should be like this. The effect of a minus 3 inside a function means right 3. Right? And then because of the plus or minus, you've got both the top half and the bottom half. I mean, it's a parabola. It's a parabola that's opening up to the right. And I didn't even wait to graph it. I just took the points that were here and reflected them across the x. I just switched the x's and the y's. That has to be the graph. And then one more I'm going to show you, just because there's some important stuff in here. So this one, the function we're starting with is a square root, right? We're not starting with a quadratic and then finding, getting an inverse of a square root. We're starting with a square root. But this, because we're starting with a square root and it doesn't have a plus or minus, it's just the plus half of it. We have to calculate a domain and a range. Now, the domain of this is x greater than or equal to 2, right? How do you know that the domain is x greater than or equal to 2? We've got to make sure we don't take the square root of a negative number. So you say x minus 2 is greater than or equal to 0, and you solve, and you get x greater than or equal to 2. The range, right? We know that a square root is positive. But, we'll just take it like this. This is the square root function, and because of the minus 2, it's shifted which direction? 2 to the right. So the graph looks like this. Shifted here, so it has a point there, and then it has a point about right there. So that's the graph. So it's easy to see that x greater than or equal to 2. It starts at 2 and it goes to the right. The range, it starts on the x-axis and it goes up from there. So the range is y greater than or equal to 0. So we got that before we start. We've defined our domain and our range. Now we'll find the inverse, right? I did the first step. I substituted the y. Okay, now I'm going to switch. Okay, how do I solve for the y since it's inside of a square root? You square both sides. X squared equals y minus 2, which means y equals x squared plus 2, right? Now that is f minus 1 of x. Okay, well, what kind of graph does that have? It's a parabola. Opens up, y-intercept is 2, right? That would look like this. About right there, about right there. Now, do those two look like they're flips across the line y equals x? No, they can't be. This is where you got to take into account the domain and the range. Remember what we said in the very first slide about this stuff. The domain of the function is the range of the inverse. The range of the function is the domain of the inverse. So if I apply those two, that means for this one here, the domain has to be x greater than or equal to 0, because that was y greater than or equal to 0. And the range is y greater than or equal to 2, because this was x greater than or equal to 2. Well, if the domain is x greater than or equal to 0, that means we don't have the left side of that. We only have the right side. Now, it is a terrible drawing of a graph, but at least now it looks like there might be a reflection across that line. That's why you have to take into account domain and range sometimes when you do this stuff. So that's it. We learned how to find an inverse, those 4 steps. You got to memorize them. We learned how to take the composition of functions, see that everything cancels out and all you get is x. That'll be proof that they are function inverses. And we know that the graphs are reflections across the line y equals x. That's it. And that is homework.